Hello and welcome back, everyone. Today we'll be going over section 5.2, integration by substitution. So this section we learn why we kept attaching that dx after the integration symbol in all those other problems. And really we can just kind of start with a couple of different notations that we've already used for derivatives. So one is dy over dx. Another notation we've used for derivative is f prime of x. Now, if we treat this as if it were just a regular fraction, we can clear the fraction and say that dy is f prime of x times dx. Integrating both sides, we get y is f of x, and of course our friend the plus c. So in this one, if we have something that's more difficult to integrate than what we've seen in section 5.1, we simply use a u substitution. So for example, they may ask us to find the antiderivative of 6x plus 1 times e to the 3x squared plus x minus 10 times dx. So this one would be a little bit easier to work with if we had something that looked like e to just one thing, e to the u. So that will be our substitution. We will let u equal 3x squared plus x minus 10. So then du over dx is 6x plus 1. Equivalently, what we'll use in integration more often is just du equals the quantity 6x plus 1 times dx. Typically, we would skip this middle step here. I just wanted to see you to see it the first time through. So then we use our substitution just like we did on differentiating. So we still have the integral. And then I'll do a little rearranging here. We have e to our 3x squared plus x minus 10 is now a u. And we also have 6x plus 1 times dx. That's the same as our du. So integral of e to the u du, antiderivative of e to the u is e to the u plus c. And then just don't forget to put your original variable back in there. The original was written in terms of x is not u's, so we get the u back out of there just using back substitution. So this is e to the u is the same as 3x squared plus x minus 10. And don't forget your plus c. That is required on an indefinite integral. So sometimes it'll take a little bit of practice to figure out what the easiest u would be for a problem. And really there's no substitute for trying those homework problems, filling up the notebooks, and experience sort of helps you find what the easiest u is for different problems. Okay, so our next one, we're looking at the antiderivative of 10x over 5x squared plus 2 quantity cubed times dx. So on this one, I see a little bit more action happening in here with the 5x squared plus 2. We're doing something to that entire quantity, so that's a good place to start with our u. So we'll let u equal 5x squared plus 2. So then du would be 10x times dx. So notice we have a 10x times dx already. So now I can make this integral of 10x dx turns into du. 5x squared plus 2 turns into u. And don't forget your third power there. So just one little adjustment there will make that integral of u to the negative third times du. And then we can just use our power rule from section 5.1. So instead of subtracting 1 from the exponent, we are adding 1 to the exponent, which means we'll need a negative 1/2 out there. And then we can put the original variable in there. So negative 1/2 times 5x squared plus 2 to the negative second plus c. You may see it written this way. You may see it written as negative 1 over 5x squared plus 2 quantity squared plus c. Don't forget your 2 outside. Either one of these are just fine as far as antiderivatives. Okay, so next up, we've seen a power rule, we've seen e to a power. Next up, we'll play with one of the other properties. So let's see, we'll do integral of x cubed plus 5 over a quarter of x to the 4th plus 5x minus 7 times dx. So after a while, you'll start to recognize some of these as being derivatives of another part. So the u here would be easier as the 1/4 x to the 4th plus 5x minus 7, giving us a du of x cubed plus 5 quantity times dx. Don't forget your dx as well. So now I have integral of x cubed plus 5 quantity times dx is the same as du. Quarter x to the 4th plus 5x minus 7, that is our u. Hopefully you recognize that format. That is our friend, the natural log. So this would be natural log of absolute value of u plus c. And then we put our original variable back into it. Natural log of quantity 1/4 x to the 4th plus 5x minus 7 plus c. So plus our arbitrary constant. So all of our 5.1 properties still hold. It's just a question of turning it from something that looks a little ugly and messy into something that looks more like the properties we learned back in section 5.1. Now, once in a while, there's a little bit of manipulation needed beyond just the u substitution. But as long as it's just by a constant, we can do that pretty painlessly. So this next one, we'll do the antiderivative of 7x squared e to the x cubed plus 2 times dx. So again, I see an x cubed and an x squared involved, so we'll make the u the higher power one, the x cubed plus 2. So du is 3x squared times dx. So you might notice we have an x squared, we have a dx. I want a 3, I've got a 7. Well, as long as this is just a constant, I can bring the constant out of the integral. I also want to have a 3. I don't have it there. So I'll multiply by 1. So I'll multiply by 3 inside, which means multiplying by 1/3 outside. That way I've multiplied by something worth 1. I'm changing the look, but not the value of what I've got. So after that, now we have 7/3 integral of, here's our e to the u, and then we have our 3x squared times dx, that is our du. Now it looks like the 5-1 problem. So now we have 7/3 e to the u plus c, and then we would just plug our original back in. So 7/3 e to the x cubed plus 2 plus some arbitrary constant. Okay, this next one involves radicals. Antiderivative of x over square root of x minus 5, all of that times dx. Now the argument of the square root will make that our u. So we'll let u equal x minus 5. So du is equal to 1 times dx, or just dx. So far so good. I see an x minus 5, I can replace that with a u. I see a dx, I can replace that with the du. That leaves us x. Well, what I can do is solve my let line for a different variable. If u is equal to x minus 5, then x can be replaced with u plus 5. So now we have the antiderivative of u plus 5 up top. X minus 5 is a u, and since it's under a square root, also 1/2 power, dx is replaced with du. And then we just split the fraction. So integral of u over u to the 1/2 plus 5 over u to the 1/2 quantity times du. So u to the first over u to the half is u to the half, plus 5u to the negative 1/2 times du. And then we just do the antiderivative one piece at a time. So u to the 1/2 using the power rule is now u to the 3/2. Add 1 to the exponent in the form of 2/2, which means I'll need a 2/3 out there. That way when I differentiate, 3/2 times 2/3 gives me the 1 out front that I had. We'll hang on to that 5, u to the negative 1/2, add 2/2 to that, and you're at a positive 1/2, which means I'll need a 2 over 1, or just 2. And of course our friend the plus c. And then it's just a question of dropping our original variable back in. So this antiderivative would be 2/3. U is x minus 5, so 2/3 x minus 5 to the 3/2 plus 10 times x minus 5 to the 1/2 plus some arbitrary constant. So if you do see something that doesn't quite fit, see if you can rearrange your let line to help it fit. All right, so I'm going to have you all try one from the book. We'll do integral of x square root of x plus 1 times dx. So give that a try, pause the video, and play it when you're ready. Okay, welcome back. So here, hopefully, you notice that typically if we have something under a square root or inside of an exponent of base e, that was usually our u for that problem. Du for this problem would be 1 times dx, or just dx. And if u is x plus 1, then x is u minus 1. So we have integral of u minus 1 times u to the half dx is the same as du. So this one, just a little bit of distributive property, gave us the integral of u to the 3/2 minus u to the 1/2 quantity times du, and then just antiderivative one piece at a time. So 3/2 power, add 1 to it, and we have a 5/2 power, which means we need a 2/5 out front. Hanging a sign in between, u to the 1/2 is now u to the 3/2. So we'll bring 2/3 there. Don't forget your plus c. And then we'll just finish it out, putting the original variable back in. So 2/5 of u is the same as x plus 1. So 2/5 x plus 1, quantity raised to the 5/2, minus 2/3. U is the same as x plus 1, now raised to the 3/2, and plus some arbitrary constant, plus c. So that should give you enough to play with the problems in section 5.2. If you're having any issues with the homework, please feel free to send me an email, ask any questions you need to, and I can work with you. So 5.2, 9 to 49, every other odd. 59 through 75, also every other odd. And that's both for the old book and the new book. Until next time, stay safe, and we'll see you then.